interval, it's lower. So one of the cool things about this is that in the coding, you can make it more simplified and you can customize it the way you like. I made these two graphs, and these two maps, I'm sorry, and you can see here that it's a lot of green. And if you simplify it, like I did over here, you can see that the, what is it, the spectrograph? What is it?
Scale.
The scale is a lot more smooth.
What's that?
It's probably a lake or something. And one of the cool things about this, one of the cool discoveries I made about this is that if you look at the Suez Canal, you can see a lot of red there. And that's usually because there's ships there. And I thought it was really cool because it was collecting that data as well. And another thing is that, like I did over here.
It's like a speech jam, right?
There's a, it's either a 3 or 10-second auto delay that you can't change.
So here we have, of course, the gain value for a turn plotted against the transmit pulse major axis. Basically, these are some of the 4 variables again. And so now we're graphing variables directly against each other. We don't necessarily expect any sort of correlation between the 2 variables, but when we plot them against each other and measure sea surface anomaly as the color on the graph, we can actually see, the first graph we did was on the left, we could actually see some sort of trends where there were bars, especially around maybe 94 meters for the transmit pulse major axis. You can see there's kind of a bar where the sea surface anomaly is higher than normal. And then there are some bars on either side of it that are lower than normal. And so what we did is we basically made the scale more specific. We focused it down a little to get an image with more contrast, basically. And you could see very distinctly that there was, in fact, a ridge there. And so this is also interesting data that could be corrected because
this side's good. Maybe
over a large set of data.
First the north side.
What am I doing?
Oh, yes.
Here, you can see it here.
Oh, are we able to turn this one to face?
Yeah, we can turn these.
Okay, so here we have the received energy by gain value per turn. It's sea surface anomaly. Basically, on the bottom here, we just have the received energy in joules, all very, very small amounts, the negative 14. So basically, we plotted the 2 graphs against each other and did the same thing with sea surface anomaly. And on the graph on the left here, you can see it looks pretty insignificant. There's a large blob of green on the left where it's pretty close to sea surface anomaly. More or less what you would expect. The only notable thing there was counts at the minimum, or measurements at the minimum level for the sensitivity of that instrument. Tended to receive very low sea surface anomaly.
We can turn it
and that continues throughout all of these. Of course, they're the same data.
If we need to.
But then we tried focusing a little more. First, we broadened the scale, or narrowed the scale, sorry, to try and get an image with more contrast. And,
Okay, no, that really helps.
You can see actually here that there is a band here of area which is below what you'd expect for the sea surface anomaly. So there are actually some details within that small curve, which is hard to identify. Here we just focused the image some more. You start seeing more and more random data appear as we narrowed down the amount of data we were averaging. But it did help us get a clear image of the main body of data. Go to the next slide. And so then basically what we did is we just took the graph, expanded it, and focused on a little part of it. And this is the from 0 to 0 to 2e to the negative 14th joules, of course. And so this is just the very narrow range, and you can actually see here now that it's expanded and we have the higher contrast that there is a very clear trend. Right around green is where you'd expect. Sorry, my head's too rich. I need a pointer. Does that actually have like a good?
It's much better.
Okay. So you can see. Oh, sorry, my hands are all gross. You can see here that this is right around 0 on the graph, but then there's a large area of this column that actually is below what you'd expect. So it has negative sea surface anomaly. It's lower than what we would expect. And there's an area over here that has higher than average sea surface anomaly. And so both of these could be attributed to errors in satellite measurements. We need this to like good. Next slide. And so then this is the last thing in the graph. This was just reflectivity. It's basically a ratio. I mean, there's a complicated way to determine it, but it's basically a ratio between the energy that the satellite puts out and the energy it receives. And you can see it's very similar to reflectivity. It's very similar to reflectivity. It's determined with reflectivity. And so we see a similar pattern. We had very specific. We had some error values here. We remember to discuss the error values. You didn't? Okay, so yeah. So these are the error values for reflectivity, which again were plotted here just for the sake of including them. But then we had a broad scale, and we gradually refined it to become more and more detailed. This has a lot less error measurements, really. And you can again see that there is that bar at the minimum measurement for sensitivity. There's a bar a little below.
You point that laser pointer at the camera again, taking that laser pointer away. I saw it on the screen.
Nice.
No one's watching.
Okay, so
You're
the
watching.
first bias that we found was from the graphs. I need a laser for the other thing. Okay, wait, I need to get this down.
You should probably just leave it on.
Wait, where's the? Okay.
That's too sad.
The first biases we found were from the graphs. The first one was, this is like stage lights. Give me a quarter. The transit pole's major axis, we noticed that C-surface anomaly is slightly below what was expected. Next one, for gain value for return, we noticed that C-surface anomaly is slightly below what is expected, especially around 130 counts. We got that from the graphs again. The third one was received energy. Received energy. So we noticed that as received energy increases, C-surface anomaly decreases rapidly. This starts at 1.5 e to negative 14 joules, and C-surface anomaly continues to decrease as energy increases. The fourth one we found was reflectivity, and we saw that as reflectivity energy increases, C-surface anomaly decreases rapidly. And again, this starts around 0.75 reflectivity, and after that, C-surface anomaly continues to decrease as reflectivity increases. Received energy. So we notice as received energy increases, C-surface anomaly decreases rapidly. This starts at 1.5 e to negative 14 joules, and C-surface anomaly continues to decrease as energy increases.
You might just want to use that one.
Well, no, that wouldn't work. It's fine. I'll just point. I don't
Well, there's another one in there. It won't be able to, Jordan, it won't be able to click, but you can probably get the, let me see,
Take the,
USB out.
yeah.
Try it now.
Good.
So, well, that's good. So you can have one for every person. So, then additionally, for some of the other biases, these were the graphs were plotted 3 variables against each other. You can see that the okay, stop! I shouldn't have given everyone a laser pointer. You can see that the gain value for return by the transport pole's major axis. You can see that as the major axis increased, there were a number of like fluctuations as we saw. It kind of went below.